Good afternoon. It's my pleasure to welcome you to this virtual symposium and our celebration of the reopening of the Detroit Observatory. As you know, this iconic building was the dream of Henry Philip Tappan. As the university's first president, he was determined to differentiate Michigan from other colleges around the country. And the way to do so was to proclaim that scientific research would be the core of the institution's work. It was a revolutionary idea at the time. The observatory was the embodiment of Tappan's vision, which has been realized in countless ways through the decades. Today, Michigan conducts more research than any public university in the country. Several of my predecessors in the president's office have been instrumental in the life and rebirth of the Detroit Observatory. In particular, we owe a debt of gratitude to President Jim Duderstadt and the late interim President Homer Neal for supporting and guiding the restoration of this magnificent facility in the 1990s. Thank you also to Terry McDonald and Gary Krentz at the Bentley Historical Library for your stewardship of the observatory, particularly given the challenges of managing a restoration during the pandemic. The university has seen tremendous change and growth since Henry Tappan in the 1850s. Yet, we remain deeply committed to the research enterprise. The observatory not only reminds us of our history, but also serves as a place that encourages exploration and the sharing of knowledge. I am particularly pleased that with this renovation and expansion, we can welcome students of all ages to learn about the history of astronomy, astrophysics, and more. The observatory came to be because of generous donors based in Detroit who believed in Tappan's vision. Philanthropy again was critical to the 1997 restoration. And today, nearly 170 years after the first telescope peered into the heavens, donors continue to play an indispensable role. Thank you for believing in the work of Michigan. I particularly want to thank Judy and Stanley Frankel for their generosity. We are honored to open the Judy and Stanley Frankel Detroit Observatory to the public. It is a gorgeous, functional place that embodies the past while always looking upward and into the future.
Good afternoon. I'd like to add my welcome to that of President Coleman, and I most certainly want to thank her for her remarks. I'm Gary Krenz, and in truth, I stand here today because of Mary Sue. After working in the president's office for many years, I had the privilege to be appointed by her to direct planning for the university's bicentennial. And really, as a direct result of that celebration, the university made an ongoing commitment to continue the work of promoting programming to disseminate, celebrate, and explore university history, its good and its bad, and that will be a key function of the renewed Detroit Observatory. It feels great to be getting underway with that today. The Detroit Observatory was completed in 1854. It expanded in 1868 with the director's residence, and more significantly in 1908 with a large academic wing, including a bigger dome. But even as early as the 1860s, there was talk of moving it. And as the 20th century progressed and astronomy found friendlier skies elsewhere, it was gradually chipped away at and continually threatened with extinction. The 1868 residence was torn down in the 1950s, the large academic addition in the 1970s. Given the university demands for space, it is a miracle that the original building survived. I want to acknowledge people, I'm sure I won't catch everyone, who were responsible for saving, restoring, and maintaining the observatory, starting with Orrin Moeller and Albert Hiltner, who as chairs of astronomy regularly resisted efforts by others to get a hold of the land. Nick and Peggy Stenek, who consistently promoted the value of the observatory and who stewarded it as tenants. Pat Seitzer, who advocated for its restoration, helped oversee it, and helped finally to return the Fitz telescope to use because, as Pat says, lenses, including historic ones, will deteriorate if they don't see starlight. As President Coleman mentioned, Jim and Ann Duderstadt and Homer Neal, my mentor and friend, who spearheaded the mission to restore it. Very importantly, Sandy Whitesell, who so rigorously oversaw the beautiful restoration as a real calling and who led the observatory into the 21st century. Fran Bluen, an early advocate of restoration, and the person who brought the observatory under the wing of the Bentley Library as a three-dimensional archive when it badly needed a home. And of course, Karen White, who has been a faithful steward and who expanded observatory programming and from whom I have learned a lot about the observatory. Too many of these people are gone and are missed, but their legacy in the building just up the hill from where I am sitting right now is great. And now another rebirth, 2022, to be added to the years noted a moment ago on the plus side of the ledger. So here we go. In terms of getting going, just a little aside, I want to say a word about the observatory's new student docents. Those of you who are attending the event at the observatory tonight will meet some of them. We hired them just 2.5 weeks ago, and they have done a truly extraordinary job preparing in a short time for this event. So if you do visit tonight, please give them a special thanks. Now it's my pleasure to introduce Terry McDonald, the director of the Bentley Historical Library, whose own vision and work made this edition possible. Terry, as many of you know, has directed the Bentley since 2013. Before that, he served for a total of 11 years as Dean of the College of Literature, Science, and the Arts. He is Arthur F. Thurnau Professor of History and is an award-winning historian of the United States. He has a Guggenheim National Endowment for the Humanities and U of M Humanities Institute Fellow. He is the author or editor of 4 books and numerous articles. Terry, take it away.
Thank you, Gary. It's a pleasure to be here today at this wonderful occasion. During the long planning process that led to the opening of this marvelous new addition to the Detroit Observatory, we referred to the process as building a 21st century portal to a 19th century experience. And physically, that certainly is true. The beautiful addition opening today is state-of-the-art in technology and facilities, and it does play the important role of leading us to the original observatory building itself, standing as it was with its mid-19th century architecture and equipment. But we also had a broader definition of what we mean. The portal is not just a passageway, but an intellectual invitation. An invitation to the ongoing consideration of how the history of the university informs and impacts the present and the future. Everything we do in the new edition will be connected to the broad question of the University of Michigan past and present, its students, disciplines, research, teaching, and persisting dilemmas. As a tour through the original building demonstrates, the University of 1854 was a radically different place. Only 17 years old in Ann Arbor, small, all male, with required daily Protestant chapel, a lockstep curriculum, and an all-male faculty composed primarily of Protestant ministers. The originally isolated 1854 building is now surrounded by the sprawling 21st century university that is massive, coeducational, secular, astonishingly broad in its intellectual research and curriculum, research-driven and faculty-centered. But the history of every institution is a series of trade-offs and complications, and our institution has certainly had those. There are inevitably great triumphs and significant failures in the history of the university. But the modern research university lives in the future. The next freshman class, the next semester, the next graduating class, the next research publication, the next project. And this is the way it should be in a place like the modern research university. But if we are only focused on the future, we can lose track of where we came from and the values that initially guided us here. We are all, individuals and institutions alike, connected to and shaped by our past, both the good and the less good in them. And it is illusory to believe that we can move into the future without understanding that past. The university needs a place to consider the past, and I'm delighted that the new Detroit Observatory complex will provide us with such a place. So it's my pleasure today to briefly thank other people that, other than those that Gary has mentioned, who shared in the vision of a place and programming in that place that unite past and present to shape the future of the university. Alums Judy and Stanley Frankel were willing to support this vision financially from the very beginning and it quite simply would not exist without them. More recently, alum Thomas C. Jones has made a major contribution to support the work of undergraduate students in this enterprise. Hardworking staff members from the Bentley Historical Library spent countless hours planning the edition, and these were Nancy Bartlett, Brian Williams, Gary Krenz, and Angela Clark. Our wonderful architects from HED brought out the best in the planning, and our construction firm, AZ Shima, did a wonderful job of working out the best on a very difficult site at a difficult time because of the COVID pandemic. Gary and Jeff Walter from the Bentley actually supervised the construction effort from day to day. University staff members from its architecture, planning, and plant areas were deeply committed to and helpful in the project, as were the faculty, staff, and community members who attended visioning sessions early on that helped us plan this place and its activities. We are fortunate to have someone as deeply steeped in the history of the university as Gary Krenz, former executive director of the university's bicentennial celebration in 2017, to serve as first director of the new addition and observatory. Today's symposium is an example of how the programming at the observatory will work, moving as it does from past to future through the series of panels and the keynote address this evening. The first panel, which I am pleased to moderate, asks an important historical question in what may be a surprising way. What exactly was science circa 1854? Our first speaker, Henry Cowles, has asked that question directly in his widely hailed recent book, The Scientific Method, An Evolution of Thinking from Darwin to Dewey. That book argues that the scientific method that we think of today actually evolved over the course of the 19th century and was perhaps crystallized by philosopher John Dewey in the early 20th century. For most of the 19th century, then, how science was to be practiced and what it actually was varied and sometimes a matter of contention. Professor Cowles, who was in our history department in LS&A, is widely published on the topic of 19th century science in exactly the same time period as the heyday of the Detroit Observatory. Our second speaker, Gary Krenz, is known by many of us as the leader of our successful bicentennial observation, as he and I have mentioned. But perhaps less well known is that he's a trained philosopher and that he has taught in our philosophy department for many years, including a course on whether the University of Michigan is a moral institution. Along the way, he has made a careful study of the ideas of Henry Philip Tappan, the man who we think of course, primarily as our first university president and the founder of the observatory, but who in his own time was a real intellectual and someone who thought of himself as a natural philosopher. I'm sure these presentations will provide us with a really great context for the period in which the observatory itself began. So on to you, Henry.
Thank you, Terry. And it's just such a pleasure to be here and to be sharing in this both retrospective and prospective. I'm hoping that here they are, the slides. And Carl, I promise I'll get my mouse out of there. I'm hoping just to provide us with a little bit of a moment in time, essentially. So to give us 1854 in the evolution of how science was practiced and how it was thought about in the United States in particular, but with, as is required in the 19th century, glimpses elsewhere. The dialogue was always international, especially before the turn to the 20th century. I'm putting this up here. This is the book that Terry mentioned, not as a plug, though it is available for free from the University of Michigan Library, but to remind us that the story that I'm about to tell is just a snapshot. 1854, A Space Odyssey, plops us down essentially in the middle of the story that I told in this book. That story goes from the late 18th century through to the very early 20th century, as Terry alluded to, and argues for a broad evolution in how science was thought about in that period. By taking a moment in the middle, what we're going to see is a series of debates or contestations within which science was practiced by a whole range of types of people in different kinds of institutions with competing ideals, and of course, and this is where we're going to kind of touch down, with different and diverging material constraints. And so this is the story in which I want to situate the Detroit Observatory amidst, as you'll see, three different evolving discourses, but also concrete practices in the context of 19th century science. So we're going to start by thinking about what we might all think about initially when we think about something like an astronomical observatory, which is to say, the observation of natural phenomena. And what we're going to see here is that through the observation of natural phenomena, which is central to the identity of scientists or men of science or natural philosophers as they were known in the early to mid 19th century, was this accumulation of facts, an extremely empirical or empiricist orientation that's gradually giving way to something else as the story unfolds. In part two, we're going to see what happens with all those facts, the data that are accumulated in this context. That is to say, the sciences broadly becoming more numerical and quantitative, and also becoming more computational. And you'll see what the kind of surprising results of that sort of work around which these astronomical developments were occurring. Finally, we'll end up a little bit later in the 19th century, though really still glimmers of this are there right in 1854 as we're taking off, with the rise of predictive science in its more or less modern form. And so here what you're going to see is the development of theories based on the computation and observations of the sort that are coming out of the Detroit Observatory, but then also pushing forward and kind of eventuating in astronomy as a more experimental science, which we'll see by the end of our short time together. So as I say, let's get started thinking about observation itself as something at the center of science. The value placed on empiricism and observation, often explicitly devoid of hypotheses or theories, is where the story in my book begins, and it's really where the story of Anglophone, that is British and American science in particular, was in the early to mid 19th century. Practitioners prided themselves on not getting ahead of themselves, not getting out over their skis, and instead gradually and patiently accumulating facts. This was often expressed as a kind of anti-French sentiment. The French went too quickly, they were too radical and revolutionary. The British and the Americans, by extension, were instead more patient and calmer. This ends up getting embodied in very concrete and physical terms in a series of institutions founded from the 1830s to the 1850s, the most famous of which, of course, is the Smithsonian, the marquee building of which was built and finished on the Mall in 1855, so exactly at the same time as the Detroit Observatory. Now, there is some contest in the building of every institution over what precisely it is for. What tends to win out in the context of the Smithsonian in these early years is the accumulation of artifacts and facts. In other words, the gathering and storage of data. Yes, there are research wings, and yes, the research is what is producing those facts, but the denizens of institutions like these prided themselves on essentially being scientific collectors. And here's a version of what that kind of collecting might look like. The Coast Survey is another prototypical mid-19th century American scientific institution. Many countries had similar surveys. The idea is to gather minute data about depths, but also about longitude and latitude on the open ocean, and then of course, all over the coasts of the rapidly expanding United States. So what you see here in dim form is the set of extremely exact measures that might produce this kind of data, which are then collected in charts and used for all sorts of practical applications. I do want to highlight here that the problem of longitude, literally the problem of figuring out where you are with respect to longitude, with respect to that measure, was only recently resolved in the 19th century. It depended on a series of material advances and clockwork. It's something that's really hard to get our minds around now, but the resolution of the problem of longitude helped this kind of boom of numerical data that we'll see getting computed in the second part of the talk. So the reasons for the value placed on observation and of the accumulation of data like this were scientific, intellectual, philosophical, as Gary might touch on, but also, of course, economic and political. It really mattered for governance, for all kinds of projects of empire that were taking place in this moment, and for literally navigating the country to know exactly where you were and to know exactly where you were going. These are the kinds of physical, earthbound calculations that the astronomical data being gathered at the Detroit Observatory and other institutions were incredibly crucial for. So yes, we are in 1854, a space odyssey, but of course we want to remember that a lot of that space data is in fact about life down here on Earth, the mundane matters of navigating, as you can see here, the Keys on the Florida coast. And one thing I want to highlight is that this obsession with fact gathering and observation is not, of course, limited to the physical sciences or to astronomy. So here what you see a little bit closer to my home, that is to say the history of psychology and the human sciences, is the array of new apparatus for studying the human mind that's emerging and essentially taking over the field in the mid to late 19th century. These apparatus are extremely carefully constructed, largely in Germany, and then imported by 2 generations of graduate students who go over to train in the new laboratories at Leipzig and others, and then bring them back and found new departments of psychology in the United States in the mid to late 19th century. 2 things to highlight here just about this kind of quick glimpse into this other science and its obsession with exact measurement. One thing is that the obsession with measurement is, of course, changing the way that the sciences themselves get conducted. So as the capability, whether through a telescope or through any of the apparatus you see here, to define parameters or phenomena more and more fine-grained takes off, what you get is a new obsession with that very measurement. And so in some fields, you have a set of people who are kind of concerned about what's happening to the larger questions, the bigger picture. You get, as you'll see in a second, a kind of division of labor, where people are more and more exactly gathering data, and then it falls to others, administrators, or people who really have no interaction with the data or with the data gathering whatsoever, to produce the computations and the theories that come out of them. So that's one thing to note about these apparatus. The other thing to note is that on the back right, what you're seeing there is a new kind of chronometer, which is exactly the way that these kinds of time measurements had finally been standardized towards the end of the 18th century. The standardization and rendering exact of the measurement of time enables all kinds of things, including the solving of the problem of longitude that I referred to earlier. Literally, you need to know exactly what time you've made an observation and exactly what time it is back home in order to solve where you are on the Earth's surface. But of course, in psychology and other fields, the exact measure of time takes on new significance as well. And so what you would use these apparatus for in the context of psychology, in the emerging context of biological research, is the exact measurement of biological or psychological processes in terms of time, which again, I just want to remind us, this seems so obvious to us now, but this is actually a new turn towards the defining of observational phenomena, of the data that you're keeping, in more and more exact measurements that give way to the rise of computational science. All right, part 2. As these observations are being built up, as more and more data are being gathered, and as problems of literally logistical problems of where to keep the data are being solved in industrializing spaces and in the context of the emergent American Research University, you also have an interesting kind of other rail to this story. This is the rail of the Industrial Revolution, of the rise of factory production, the industrial economy that's taking off in the Northeast, but also, of course, in the changing and standard industries in the Northern Midwest as well. So here you see Stroh's Brewery, which is expanding rapidly exactly in this period, despite the temperance movement and the kind of precursor to Prohibition, toward the kind of things that we end up celebrating in Detroit industry on the model of the assembly line and factory production. What does this have to do with science? Well, on the one hand, of course, this is a reminder that science doesn't just happen in university settings. And in fact, for most of the 19th century, it mostly doesn't happen in university settings. It mostly happens in industrial settings. And so what you're seeing here is actually a window into the place where these other laboratories are occurring. Gentlemen scientists are still the major figures in gathering a lot of this data through the early part of the 19th century, leading into these institution building efforts in the mid-19th century. So this is one reminder of where science is actually still taking place in the 1850s. But it's another reminder that as these universities reform and change, as Tappan's vision is realized, as Harvard and Yale reform themselves on the scientific and slightly German model, another place that they're looking is to industry itself. One of the things that you're seeing here is the rise of a way of dealing not just with the data that's being produced, these masses and masses of paper-based ledgers, but also with the people producing the data that's more like the emerging division of labor you're seeing in the factory system applied in a scientific context. And I'll come back to the kind of consequences of this in a second. Now, of course, in exactly this moment, there are all these fascinating visions that even casual historians of science recognize as extremely important. Some of these visions are about the actual literal mechanization of knowledge production. And so a famous example is the case of Charles Babbage and his dreamed about difference engine, or there is some contestation about whether he in fact built one. He never built the analytical engine, which was his second project. The idea being that you could produce and mechanize human thought, thus freeing us up, humans that is, to doing other kinds of cognitive labor. But if we step back for a second, Babbage's dream of mechanizing some part of science and the increasing data that you're seeing in what Ian Hacking has called the avalanche of printed numbers is producing something like a crisis. What do we do with all this data? We've all had this experience of collecting and then never looking back at the things that you've collected, of downloading things from the internet that you never read, or of having 52 tabs open in a browser and never getting to them. I want you to think of the scientific researchers in this period, the period of the founding of the Detroit Observatory, as very quickly confronting this dilemma. And what it produces is a change in the way that labor in science is understood and that division of labor that I referred to earlier. This is an important point to remind us that the original computer, of course, was not mechanical, right? Babbage was imagining replacing the original computer, which was a human computer. Computation, of course, was a human skill that he worked very hard to put into the machine. And that's still a vision that exists through to this day. But there is always also still human labor, often hidden human labor, behind the scenes of any computational exercise. So what you're seeing here are the famous Harvard computers, a female core of workers working for the Harvard Astronomical Observatory in the late 19th century. But this is just a reminder that all that data being produced, and then its kind of second road into the world of theory that we'll get to in a second, is always through this annulus of human labor who are codifying it and computing it for the use of scientists and for those economic and political predictive powers that I was talking about at the beginning. So again, just to come back to this psychological example where you saw those apparatus in the beginning to see that in fact this isn't just an astronomical or physical phenomenon, but it's happening across the sciences, what you get is a series, an increasing pile of studies like this one, where what's now being measured is very minute differences in reaction time of human subjects based on where they're paying their attention and which kind of apparatus they're using. Sensory and motor differences, differences in kinds of light stimulus. The point for us is that this ability to deal with this amount of data, to be fascinated by it, which is to say, to not be bored by acquiring it, but also to run the kinds of computations that produce usable information for example, advertising products to human consumers, becomes paramount. I want us to think of this transformation from about 1854, where we're starting, to the end of the 19th century, as a fundamental transformation in what matters in science. If we begin with pure observation, with no eye to theory and computation, at least theoretically or ideally, you'll see that that's not the case in a second, we end with the kind of prioritization of a form of statistical sight that is still with us. The ability to crunch the ever-amassing numbers of astronomical and other sciences ends up taking over by the end of the 19th century. Which leads us to what happens to all those computations. And the answer is, to a certain extent, theoretical predictions, which end up folding back into the observational world with which we began. So let's think about how that folding works, and let's think about it not in the context of a numbers-driven field like astronomy is becoming, but instead it's something that seems totally anti-numerical. Let's say natural history. A great example of theoretical predictions cashing out or producing changes in observation and ultimately in computation is Charles Darwin's famous 1862 prediction on the basis of a flower discovered in Madagascar that a hawk moth with exactly the right length proboscis, which you see here, would end up being discovered to explain how that particular flower was pollinated. The moth was not known. It was discovered 20 years later. This is an example of a theory, evolution by natural selection, producing a prediction that ends up cashing out in observation because naturalists know what to look for. And that's the kind of looping that we're going to see over and over again in this mid to late 19th century moment. Another, perhaps even more famous example comes in what you might call the death of the theory of the luminiferous ether. For centuries, an ether, an invisible, immaterial, but also strangely material substance existing all around us and all through space, was posited as the medium through which light traveled from the sun and other stars. It was a fundamental idea in astronomy. It was also fundamental to theoretical physics. But over the course of the 19th century, as more and more minute observations were made with telescopes and other instruments, the computations rendered with those data ended up producing very strange paradoxes in the science of the luminiferous ether. By the time of 1881, in the famous Michelson-Morley experiment, the apparatus for which you see depicted here, the supposed ether drag, or a phenomenon that it would be kind of theoretically required of this existent ether in terms of the way that light would bend around massive bodies, was disproven. So what you have here, right, is a series of observations taken at astronomical observatories and others, computed out to the nth degree, producing extremely precise predictions, which were then experimentally debunked. This is one of those things that I meant when I said it's becoming quantitative, but also it's also folding back in on itself, and the very meaning of science itself is changing. Now, in the context of astronomy, there's some really interesting work going on in exactly this mid-19th century moment that the observatory is founded. So perhaps the most interesting case is this idea of the personal equation. What you have here is a very simple fact. Astronomical observers, as measurement becomes more precise, are seen to diverge slightly in their measurement of the location of particular stellar phenomena. What's interesting from an astronomical and a psychological perspective is that astronomers seem to diverge in patterned ways. You might be 2 clicks to the left or 2 clicks to the right routinely. This matters as measurements get more and more accurate and as more and more industrial and political uses depend upon exact measurements. So what you have here is a very carefully controlled Parisian experiment in which the astronomers or the observers' exact personal equation was measured against each other and against an objective backdrop. They actually produced a fake stellar phenomenon, a fake transit of Venus, in order to measure just how far off the observers were. The idea, importantly, was not for those individuals to correct their personal equation, that is, to become perfectly accurate, but for a meta-observer, that scientist I said, right, who's no longer doing the observing, but is collating the data or computing from the computations, to know, oh, that's Henry's observation, he's 2 clicks to the left, and to correct for it. So what you have here is astronomy and observational science becoming experimental to solve a problem of human error, but not asking the humans themselves to solve it. This is the era, or the dawn of the era, of what Lorraine Daston and Peter Gallison call mechanical objectivity. That is, the exact melding of the human and the machine, or the kind of mechanical idealization of human observation. So these astronomers, again, are now part of the apparatus. And this again speaks to that idea that there's a division of labor where you have observers simply recording what they observe, computers, in this case often women, computing or initially collating the data that's being observed, and then increasingly leaders of institutions producing the theories based on all of the labor that's happening, often invisibly, just beneath them. Finally, or semi-finally, to return to this context of psychology, to think about what all this means for the practice of science and its personnel in the mid to late 19th century. One effect of this emphasis on exactness, of the increasing computation, and of the recognition of human error in the face of perfect computation is the isolation of science itself. In some cases, this means isolating it from political concerns, or at least trying to, and in others, as you see here in the famous isolated room, it means isolating the researcher away from others to avoid distraction. This is a graduate student depicted in an isolated room conducting one of those sensory experiments that I talked about before, but you can see this also as a metaphor for what happens to science, both in its practice, what it is like to actually do science in this period, but also, importantly, in its public image. So where does this leave us in terms of thinking about science circa 1854? I want to leave you with 3 really quick ideas. The observations taking place at the Detroit Observatory and others shape the computations that are possible. This gets back to the old principle of garbage in, garbage out. The data you have end up shaping the computations in often unacknowledged ways. Those computations tell you which kinds of predictions you can make and which you can't. The computations that are available end up pushing the field in some directions and making others seem less visible. But finally, and here's where things get interesting for the historian, of course, no matter what observers say, prediction shapes observation and computation in turn. They are not conducted in a vacuum, no matter how isolated a room you lock the graduate student in. Predictions and the hopes that we invest in discovery and in navigation of the physical world will always bend the arc of science towards human interests. And that, in the end, is why it remains a human story. I'll leave it there. Over to you, Gary.
Thank you, Henry. That was great. That I really enjoyed that tremendously. So I'm going to be talking, as Terry alluded, talking about Tappan. Tappan, looking back on his time at the university, and in fact, in the context of writing to the board, to a public response to his firing by the Board of Regents, referred to the observatory with some warmth as a creation of my own. And so I'd like to explore a bit, what particularly attracted or attached Tappan to the observatory. How was it representative of his goals for the university, and how indeed was it connected to his understanding of science and the pursuit of knowledge? Now, Henry set 1854, and that's sort of the date we're focused on, right? And it's the key date here. And in a way, I'm going to take us, though, back in the other direction, because the intellectual heft of Tappan's life is really pre-1854. and a very different sort of world than the world that is developing, as Henry described it, post 1854, or in the second half of the 19th century. Tappan was a philosopher. He was a reasonably successful philosopher, if not an earth-shattering one. But he really was a product of the Enlightenment in a way, and including its romantic strain. He was closer, certainly, to a philosopher like Immanuel Kant in his thinking than he was to William James or John Dewey. And a lot of his work presents some of the paradoxes of Enlightenment thinking. But the era from which Tappan comes is the era that starts the construction of the modern university. It was Kant who articulated the fundamental principles of separation of the philosophical or scientific faculty from the constraints of church and state. Inquiry should follow its own free course. It was Wilhelm von Humboldt who founded the University of Berlin in 1810, when Tappan was 5. Based on those principles, and Henry Tappan sort of absorbed something like this view of what a university ought to be. In that view, such a university had at its core the goals of cultivating reason and freedom. And I hope this will become clear in discussion of Tappan's thought. This is the sort of university he wished for America and the university he wished U of M to be. The development of freedom and reason in the individual, the nation, and humanity is the goal of the university. Now, just a little bit about Tappan, and here again, this is maybe looking back at the kind of world that Tappan originated from. He was born in Rhinebeck, New York in 1805. His family was long established in New York, very well connected. This is a painting of the era of the Hudson River Valley, where Tappan grew up, by Frederick Edwin Church. It conveys some of the romanticism that can be found in Tappan's own writing. He went on to study for the ministry, but eventually he wanted more. And so he went to New York City, where he joined what is now New York University and took up philosophy. This is a view of Manhattan from Brooklyn at about the time that Tappan arrived. So you can see, if you were to see a picture of Manhattan in the second half of the 19th century, it would look much, much different from this. In any case, in New York, Tappan delved more deeply into philosophy. And I want to discuss how Tappan's philosophy develops in this period, from the time he goes to New York City to the time he comes to U of M, and how in particular the theory of knowledge that he develops relates to his thinking about a university and what the purpose of a university ought to be. These are 4 key texts by Tappan. His first major and most widely read philosophical text was a 3-part work on freedom of the will, in which he engages in an extended critique of the American theologian Jonathan Edwards' doctrine of determinism, and then goes on to develop a theory justifying free will. He writes and publishes this when he is at University of New York. In the late 1840s, though, he is also formulating ideas about a university. In 1851, he publishes University Education, at the bottom left, which presents a critique of American higher education and proposes an alternative based on the Prussian model as he understood it. It was in part this book that brought him to the attention of Michigan's regents. In the meantime, he's working on a comprehensive theory of knowledge, which he ultimately publishes in 1856 under the wonderful 19th century title, Elements of Logic, together with an introductory view of philosophy in general and a preliminary view of the reason. I should say, first half of the 19th century title. And of course, in 1952, he arrives at U of M and delivers his inaugural discourse. I want to focus on these 3 texts because the inaugural discourse expressly draws in ideas from the other 2, presents in succinct form a structure of knowledge, and it presents a theory of university education to realize that structure in practice. Now, one of the big influences on both the logic and university education was the French thinker Victor Cousin. Cousin was connected with the German idealists Schelling and Hegel, and he developed a philosophical system that sought, in his view, to correct their errors, and most importantly, the errors of Kant. And importantly for our story, he was also for a while the head of the French Bureau of Education. And in that capacity, he published an exhaustive study of the German system of education from kindergarten to Universität, and that study was disseminated in the US Indeed, John Pierce, who formulated the first plan for education for the state of Michigan when it was admitted to the Union, cites it and was clearly influenced by it. And its influence can be seen in Tappan's university education. In fact, it is not unreasonable to think that one of the things that convinced Tappan to accept the U of M position is that he saw here in the influence of Cousin a receptivity to his own theory of higher education and his own interests in establishing what he called a true university. So let's start with Tappan's logic. It is a version of transcendental philosophy in the line of thinking initiated by Kant, although Tappan differs from Kant in important ways. For our purposes here, let's just say that the fundamental idea of transcendental philosophy is that human experience involves a correlation of mind or subject that experiences with a world or object that is experienced. What the mind or subject brings to the experience is all of the concepts, terms, laws, principles by which that experience is shaped or even made possible. In other words, the transcendental philosopher says, whatever sensations, images, ideas, or impressions I have at any given moment, they are not real experiences until my mind orders them in some fashion, fundamentally according to the laws of the reason. For transcendental philosophers such as Tappan, what this means is that there is a realm of objective knowledge, the world is phenomenon for the human mind, and there is a realm of subjective knowledge, or knowledge about the mind that comes from the mind reflecting back on itself. The outcome is that given that the laws of reason are inherent in mind, the basic parameters of experience can be known, and the objective world arises because of these parameters. There may be a history to human knowledge, and Tappan discusses this history, but it is a history that culminates in transcendental knowing. In other words, empirical research will continue to fill in more and more of the details, but the fundamental laws by which the mind is correlated with the world will not change. And bless us, we are living in that era. This is a very different view of knowledge, philosophically speaking, from what will emerge, toward the end of the 19th century and early into the 20th century, and perhaps under the sorts of influences that Henry was talking about, right? And perhaps we can get into that later in the session. In any case, where this leaves Tappan is that nature is organized according to transcendental laws, and this basically means that reason can logically deduce the structural relationships between realms of knowing. And this is what Tappan does in the logic, and he does it in much abbreviated form in the inaugural discourse. So here's the objective side of the equation, and here's his derivation, at least part of his derivation of various disciplines. And it's worth contemplating this for a moment. He begins with pure space and pure time. What are the fundamental elements of experience? Well, these. If you close your eyes, it's not unreasonable to think that the pure ideas of space and time could be there irrespective of anything else. So if we think about how to think about pure space, devoid of any particular content, simply the characteristics of abstract shape, geometry naturally emerges as the first science. Analysis might seem to be a little less obvious to do with time, but if you think about things like differentials and integrals in calculus, you can see how they entail, in a sense, a kind of movement, a sequential differentiation or sequential integration of this, then that, which would be of the essence of time. At least this is a caricature in a way of Tappan's derivation, which he goes into in much more depth, of course, in the logic itself. I think you already may have noticed that astronomy is the first natural science to come up because it is the science of concrete objects in space and time. It is also, Tappan notes, the oldest of the sciences. In any case, once we know something about the basic relationships between bodies in space and time, we can begin to derive other sciences, beginning with physics and so on. So this does undergird a kind of mathematical understanding of the universe, an understanding that could lead to the discovery of Neptune, say, but it undergirds it again in a much different way, in a kind of eternal transcendental way that would be very different from what, say, John Dewey would say is the way in which knowledge comes about and gets organized. So just briefly, the subjective side of the equation, this is his derivation on that side. And it's worth noting that at the top of the chain is being, right? Being resides on the subjective side of the equation, not the objective side. And that is, in the end, related to Tappan's idea about what it is to be free. So in short, Tappan derives, at least in his own thinking, an order of knowledge based on transcendental principles, principles that can be known a priori, irrespective of the empirical values that will ultimately fulfill them. And he does this for the domains of both objective phenomena and subjective experience. Now, we might ask, how does this structure of knowing get actualized in human experience? How does the human subject actually come to explore, develop, and realize the work of reason? Tappan consistently talks in the logic about two great motivators of human experience, utility and beauty. In forming our acquaintance with nature, we have become conscious of two commanding ideas, utility and beauty. The world is useful, the world is beautiful. We take from the world to meet our needs, and we appreciate the world as it presents itself to us. Then we alter the world to better meet our needs, and we learn from the world how to create things of beauty to satisfy our spirit. Because we are able to discern the laws of utility and beauty, we're able to manipulate objects to obtain even greater degrees of utility and beauty. They represent for Tappan the application of the subject's will to the objective phenomena. The subject freely alters the world. Now, with respect to the university of the time, this is really kind of a critical idea. An important debate had to do with the inclusion of the utilitarian within higher education. On the one hand, the nation very much needed training in and expansion of the practical arts. On the other hand, there were many who thought that utilitarian studies detracted from the classical purposes of education. But for Tappan, the mind is all inclusive. Action and thought are inherently linked. All of these things are manifestations of the subject's relationship to objects in terms of laws and principles, so all should be part of the university. And this was, of course, a convenient stance in a then Western state that clearly needed technological development and education, but it also genuinely springs from his philosophical disposition. So let's turn now to the discourse, his inaugural discourse at the University of Michigan, which is a call to action, as these sentences indicate. And in the discourse, he takes his theory of knowledge, this derivation of fields of knowledge, and he uses it to argue for what ought to be taught and researched at a university. He has two goals. One, to make the case for a particular vision of a university as important for this development of utility and beauty, as important as a cap for the overall system of education. This is really right out of Cousin's analysis of the German model. As important for the cultivation of the individual and the individual's freedom, and as important for national freedom and national intellectual development. So that's what the university is supposed to do. And this is the kind of university that can do that, right? It's a university free from sectarian or other constraints. When Tappan arrived at U of M, the standard practice was to rotate or distribute the professorships among the various religious denominations, right? He wants a different university, a university, as he says, of the people, not of the religions, therefore a state university. It's also a university dedicated to the advancement of knowledge, not just dissemination. And therefore it has to be, in Tappan's view, a university organized according to the entire breadth and structure of human knowing. And he says, now when we speak of a university, we speak of an institution that makes adequate provision for all this. In other words, the university is not, supposed to be, pardon me, let me back up a second. The typical American college at the time, Tappan said, is not a true university. A true university would be a place of indefinite study of all possible subjects. He was actually opposed to the idea of a 4-year bachelor's degree. It should be a place that does not concern itself with rudimentary knowledge. That would be for the gymnasium or the high school, only with advanced knowledge. And it would be a place where faculty and students alongside them work to advance knowledge through rigorous science and scholarship. And he starts to implement that vision with an observatory. Why? Well, as we've seen, astronomy was first in the order of sciences, and perhaps that played a role, but there were certainly other reasons. Astronomy was a practical science for the needs of an expanding nation, given its importance for navigation and surveying and timekeeping, which we'll hear a good deal about in the next panel today. And observatories were popular institutions. The American public, spurred on by some spectacular astronomical events, such as the Great Meteor Shower of 1833 and the Great Comet of 1843, was enthralled with astronomy. And surely, while one of the reasons the Detroit donors wanted to invest in the observatory was to get a timekeeping service, they also wanted to make Michigan a cultured, intellectually strong, and scientifically engaged state. And at the time, probably nothing said that better than an observatory. Key to realizing the vision was to develop the faculty in a more professional manner. When Tappan arrived at Michigan, the practice, as I said, was to divide the professorships among the denominations. Tappan put an end to that. He brought in Franz Brunoff as the first director of the observatory. Brunoff was already a renowned scientist, and he was the first PhD member of the faculty and responsible for an outstanding legacy in astronomy education at U of M, as we'll also hear in the next panel. In pursuing an observatory, Tappan was launching a project that, if it succeeded, would put U of M on the map intellectually and bring prestige to the university, and it worked. The observatory was soon cited as one of the top 3 in the nation. It very quickly became to be seen as the place to study astronomy, as its alum Cleveland Abbe later recalled, and it attracted many students from across the country to U of M, even those who had no intention of studying astronomy, not unlike football today, I suppose. It was very quickly followed by other developments: the creation of a chemistry lab, possibly the first dedicated to instruction on a US campus, but at any rate the largest; expansion of the collections, which had already been given a good start before Tappan; introduction of laboratory work, emphasis on independent study, and generally recruitment of a more and more accomplished faculty. But of course, all was not rosy, as we all know. Not everyone was enamored of Tappan's vision or of university commitment to research. Denominations resented the termination of the rotation of appointments. Some people thought Tappan elitist and didn't like his East Coast manners. And some thought his plan for a university was elitist, which in fact it was. All of this, and to some extent his own thin skin, led to his ouster in 1863. Not, however, before he had set the university on a course toward becoming what we now recognize as an American research university through all of the evolution during the period that Henry was addressing. So those are my remarks, and I look forward to the discussion.
Thanks very much to both of you. I think everybody undoubtedly learned a lot from putting these talks together. And let me just remind everyone who's tuned in that we're very happy to have questions from everyone in the audience. So if you have a question and you put it into the chat, we'll certainly get right to it. So feel free to submit anything that's interesting from either one of these talks or the history of the observatory itself, or whatever strikes you as worth having answered in this really kind of fundamentally historical panel. I think one of the things we're seeing in these two presentations, of course, is 2 radically different ways of thinking about science and practicing science. So we've got the kind of natural philosophical approach that obviously Tappan represents, which to some extent is quite deductive from a sort of philosophical standpoint. And then we've got the sort of increasingly empirical approach that Henry has described, and let's call that the mainstream approach, although maybe that's not a good way to put it. So let's talk a little bit about that tension. One of the things that Henry points out in his book is how increasingly science obviously becomes somewhat more professionalized, whereas in the beginning science is really performed by many people of all different backgrounds and sort of practices. And of course Tappan is to some obviously an amateur in terms of science practice, although he has a lot to say about the sort of philosophical foundations for it. So my question, to get back to it, is, and let's start with Henry and then move to Gary. I mean, so what actually happens to the natural philosophers? I mean, so people like Tappan probably aren't part of the mainstream, let's call it that, movement. Couldn't be in many ways given their training. And in fact, as you know, many of the people that were early on trained to do science were actually trained in divinity, in part because that's what you could study in those days. What happens to the natural philosophers? Is there a version of that continues? Is it just out of the mainstream or not? And then maybe, Gary, you could say something more about Tappan's intellectual life after he leaves the university such as it is. So Henry, you want to start?
Yeah, it's a great question, Terry. Historians have answered it in many different ways. And so I'll just put three kinds of answers that have been put out there, none of which is about the death of the natural philosopher per se. So the first kind of answer that people have tended to give is that in the 18th century, you see a kind of interesting parallel between the natural philosopher in the mode that Gary's just described and the natural historian, which is an identity in that period, which involves the empirical gathering of facts and Linnaeus being the prototypical natural historian in this sense. And that a large number of the what you might call the biological sciences come out of that tradition, not from the natural philosophical tradition. So you would see the legacies of natural philosophy in the university still today, in, for example, the math department, and indeed in the philosophy department. And so it's not that it goes away, it's just that the things that we tend to think of as STEM tend more often to come out of this other stream that is interacting with natural philosophy all down the road. So that's the first answer. The second answer is about the kind of a change that you alluded to, Terry, which is to say that the philosophically embedded, often Kantian or in the shadow of Kant approach to natural philosophy that Tappan stands for, where you're doing kind of a first principles thing and then giving way to the empirical study of the world or explaining the empirical study of the world, does directly inform the development of psychology itself, right? That in fact, all of the German psychologists who are using all these instruments in the 19th century see themselves as operating in the tradition of Kant and others, that they're in fact just rendering it exact. And so in a way, you see the legacies of the tradition that Gary's described right there in the sciences that are in the laboratory that look more like natural history. But in fact, they are, if you ask them what they're doing what is often they think of as a kind of experimental philosophy, but it's still a natural philosophy in that sense. Okay, that's two. The third thing, and then I'll turn it over to Gary. There is a collectivization narrative going on here, which is about labor, but it's also just a fundamental shift in science. The world that Tappan is describing, and the world that many of the figures in my book still adhere to, is that science can happen in the head of one individual. That you can think exact thoughts, that you can gather data, that you can do this, the scientific method that my book ends with, this idea of hypothesis testing, that you ask a question, develop a hypothesis, that's really framed as being something one person can do. But over the course of the 19th century, most fields of science are no longer the sort of thing that one person can do. It's teams of in a laboratory. It's that division of labor that I referred to, where literally the leader of the laboratory doesn't know how to pipette the organic substance down there on the bench, right? They've kind of lost touch with that. And so that stratification and collectivization, which leads to the rise of the scientific journal and the scientific paper and the idea of the scientific community, that's a huge transformation where the individual focus of the philosopher that Gary's describing is simply not descriptive. It's almost like that individual philosopher has been broken up into hundreds of people who are now collaborating, often across institutions. And that's modern science, is that collective enterprise. But I'll leave it to you, Gary.
Yeah, thank you. I think that's all great. I think that Tappan certainly was not unappreciative of this sort of emerging collectivism. I mean, and the sort of all his talk about facilities and all his understanding of the need to bring in people who had a different sort of training from what he had is really all to his credit. He also spends a lot of time in the logic, developing a theory of induction. Although John Stuart Mill publishes his logic a couple of years before, and Tappan is just a little sort of a dollar short, a day late with his view of inductive science. And it's interesting because as much as he was prepared to develop an institution that was responsive to the kinds of needs that you're talking about, it's not at all clear that as an individual thinker he had anything to do. He had anything to do with that. I mean, there's no real evidence that he did anything. That there was no peer review of his logic. It's not even clear to the extent to which he shared it with anybody before it was published. It really, in that sense, was kind of just his own development. I mean, he got ideas from others like Cousin, but he did not share the logic with Cousin, as far as I have been able to determine. So it really is this part of this idea, again, kind of a romantic idea of the self-expression of the thinker, right? As putting out a kind of theory in that sense. So Terry, you had asked, what happened later in his life, and it's difficult to get a really good picture of this, but that in and of itself might be revealing. I mean, Tappan was really very embittered by being fired by the Board of Regents. He essentially packs up and moves to Europe. And he really just does. There's no evidence that he really does much more at all philosophically after publishing the Logic. I mean, he appears to give some talks and so forth, but they tend to be much more culturally focused. He writes some poetry. He does some other things along those cultural lines, but and he does appear to he appears to engage in salon type fashion with others. But his productive days as a philosopher essentially ended in 1856 when he published the Logic.
Great, thank you. So, Gary, I want to just follow up on one question, which has to do with the first astronomer, of course, who it turns out to end up being Tappan's son-in-law, but who was much more in the sort of observational mode that Henry's been describing. You want to say anything about Bruno?
Well, he was, very much in an observational mode, although clearly deeply trained in mathematics and the author of a textbook on positional astronomy. Brunoff, was from Germany. He had been an assistant astronomer at the Royal Observatory in Berlin. In fact, was present when Neptune was discovered based on the mathematical predictions of Leverrier, the first planet to be discovered by prediction rather than by chance. And Brunoff, it's a good question why he agreed to come to the wilderness of Michigan to head an observatory, but he did. And he really kind of brought here this German approach to astronomy, which was highly mathematical and really based on close interactions. And Henry might know more about this than I do, but close interaction between the observation and the mathematical calculation. And in a way, what made U of M stand out at this time, what made the Detroit Observatory stand out was it was the observatory where students were both learning the math and they were getting to use the telescope under Brunoff. Harvard, they would learn the math, but they didn't get to use the telescope. So there was not the kind of, they weren't getting the big picture, the full picture. Right? They didn't have the interactive experience of actually working through the problems from observation to mathematics and back.
Great. Yeah, I think as some of us know, one of the interesting things about the observatory is it was the site of one of the first complaints, though, from students about how much time they got to actually use the telescope. And we oftentimes also forget that the corollary of Tappan's vision was to get all the students off the campus. So, the University of Michigan had no dormitories in the 19th century. And in 1856, the original University of Michigan had two big halls, which are basically Mason, today in the area of where Mason Hall is today, Mason and North Hall, and they were dormitories. And then there are also classrooms and laboratories and stuff in the same building. And Tappan decided that the space on the university had to be devoted to research and teaching and not to the students. And so basically in 1856, he got all the students off the campus. And from then on, they lived in boarding houses around the town, which on the one hand had some kind of interesting aspects. It meant the university was not in that business of in loco parentis after that. And that had some advantages for university history. On the other hand, it threw the students on the mercy of the local landlords. And that was going to make it really complicated for minority populations to find housing. And over time, successively, women and African Americans and Jews would have a challenge getting housing in the community. So there was this right from the very beginning, there was an initial tension between research and teaching in the sense in which the university would be involved in the lives of students, as other colleges, of course, were, but keeping in mind that Tappan had a place like the University of Berlin or something in mind where, of course, there wouldn't have been a dormitory in the European universities in those days. Which leads me just to ask about the question of what we know about the teaching of science in this period. As you know, the classical curriculum was notorious by 1856. for basically being memorization and recitation. It was not a deeply intellectual form of teaching and learning. And in fact, in some ways, if you look ahead, the demise of the classical curriculum was to some extent connected with that approach, that it really wasn't a deep, it was all based in the classics, but not necessarily a deep engagement with them so much as simply kind of a cursory kind of knowledge of them. So what was the teaching of science like? What do we know about that, Henry?
I mean, you're exactly right that especially in this 1850s moment, it was unrecognizable compared to the present day. And most of the disciplines that we might think of today weren't differentiated from one another. And if science came through, it was often in a kind of, for a historian of science, kind of an interesting way, where one of the things that you would be studying would be, for example, learning physics through reading Newton's Principia. So a kind of, a historical or a case-based curriculum, which was past-oriented rather than future-oriented. I guess as a historian, there's benefits to that approach, and it could be integrated even more than it is today.
Mm-hmm.
But the big transformation that you see starting in the late 19th century here and elsewhere is the involvement of students in the research process. And so, interestingly, looking back from 2022, this happens across fields. And so what happens, especially as graduate training comes online, is that it's almost an apprentice model where you go to work with the person in your field, you learn from them, but also by learning from them, you are contributing to their research agenda. So think now of being a grad student or even an undergrad in someone's lab, a bunch of papers are coming out of that you're involved in. Even on the first day that you're there, you're learning to do something and you're kind of involved, and there's questions about authorship and credit, but those are there. Today, in the humanities, that tends not to be the case. And so what we've got in the humanities and many of the social sciences, though not all, psychology is much more in the STEM category in this regard, is the tension that many faculty feel between their research agenda and their teaching agenda is partly because if you are teaching, you are not doing your research. Now we have ways of making them synthetic and syncretic, but that's the upshot of the way that humanities especially have evolved as a kind of isolated, non-collaborative field until very recently. In the sciences, they maintain this more or less apprentice and then ultimately factory-based model where you've got a head PI who's working with a huge team of people who are helping to train one another. And out of that is coming these papers such that teaching someone to, pipette, like I said, or use a PCR machine is also involved in doing research. Whereas the split actually ends up occurring and feeling more at home for the humanists and the social scientists in the 20th century. In this late 19th century moment, you had guys who were having their students translate Greek for them so that they could write books, right? And that was teaching them Greek and also doing their scholarship. So they were much more similar in 1890 than they were in 1990.
Gary, anything you want to add to that for the undergraduate side of things?
Well, I think Henry has made it clear. I mean, I agree that there is this problem in the humanities today that stems from this kind of lack of lack of a division of labor in some respect.
So we have a question from the audience that Gary knows something about, which is the famous attempted discovery of Vulcan. I guess was he the second astronomer? I'm forgetting now. Do you want to give us a little story about the non-discovery of Vulcan?
Well, I think we might hear about that in the next panel, actually. But,
okay.
But indeed, yeah. I mean, Watson took the theory that there was a planet between Mercury and the Sun was just out there. It had been predicted by Leverrier, the same guy who predicted where Neptune could be found. So this was not without credibility. And there had been numerous attempts to find this planet. And a lot of people had given up on it, but Watson decided this was going to be his next big move. So he took the opportunity of an eclipse, a solar eclipse, to try to see the planet, and he believed that he had seen it. And in fact, somebody downstream, so to speak, in the path of the eclipse also thought they saw something. So, again, peer review and so forth not being well established at this time, this all went out into the press. And so it was announced worldwide that James Craig Watson had discovered the planet Vulcan between Mercury and the Sun. There ensued a very heated debate about whether he had done that or not, and mostly the scientific community sided against him. But he actually went to his premature grave thinking that he had discovered Vulcan and trying to find ways to replicate the observation.
Interestingly, that debate, and of course the scientific sides in that debate, I mean, it's interesting how that was all being conducted in the 1870s. I mean, it was actually a kind of interesting example of how different frameworks on observational science could be brought to bear on a real question: is there a planet there or not? Anyway, kind of interesting how astronomy was playing that role in the general, kind of sciences, where so many other fields were doing all kinds of observation, everything else, but they weren't necessarily having an impact on the way the discoveries of the field were being interpreted or looked at.
Well, I'm sorry, and the debate was, a lot of this was just carried out in the press, right? I mean, this was just in newspaper articles, and I mean, I don't know, Henry, is that I wonder if, Henry, if you have anything to say about that in terms of sort of the development of science at the time.
Yeah, I mean, so peer review as a standardized system that's involved in validating claims is non-existent in that moment. I mean, some people try to do it a little bit ad hoc, but the major journals that we're familiar with still today are being founded right then, and they're kind of just getting off the ground and competing with one another. You're just as likely to read about a major discovery in the newspaper as in the transactions of the Royal Society, for example. So, all of the kind of material paper reality of scientific claims is only just lurching into existence. And it's so different from the current moment where if you ask any, especially someone in the STEM fields, if you ask them, what do you spend your time doing? The thing they'll bemoan first, the thing they'll describe for, I mean, they may not bemoan it because they have to celebrate it because they benefit from it as well, is this peer reviewing they do for other papers in their field, which takes up a huge amount of time, is often conducted for-profit companies who are selling subscriptions to these journals for thousands of dollars to institute. I mean, librarians know this reality. It's a vicious circle, but it means that a lot of that unremunerated labor is a kind of pay it forward model where your claims are going to get validated through this process, and then there are just these holes where the replication crises across a couple different fields over the last 15 years remind us that the kind of externalizing of those checks into the literature, especially when people are so bogged down and burnt out and trying to do multiple of these a week, it creates problems. And so that's, it's not that the system that we have in place now is perfect, but it's much more regularized than it was in the 1870s when it essentially didn't exist.
We have another question from the audience. Gary, this will be touched on later too, I think, but you might want to give a brief overview of this. Why in the world were Detroit businessmen interested in the observatory?
Well, I think there were two reasons, and I mean, I sort of just touched on them in passing. One was the ability of the observatory to set time, and that was actually the idea of Henry Nelson Walker, the lawyer and railroad magnate, as it were, who went up to Tappan and said, how can we help? And Tappan says, let's have an observatory. And Walker says, well, if we're going to do that, then let's get a second telescope that we can use to set time. I mean, businesses needed consistent time setting. The railroads did, but so did shipping companies and so forth. So that was one reason. But most of these donors were part of an organization that was devoted to promoting knowledge and culture in Detroit, and they had a genuine interest in the promotion of science in and of itself. So there was that motivation as well.
Yeah, I was going to say this is really interesting. I mean, this guy was the former Attorney General of the state and attorney for the railroads. I mean, this organization was a classic example of amateurs who cared about science. I mean, they were having these meetings and having papers read and all these kind of things. A very, very interesting kind of community-based science that you've talked about in the early period, Henry. That kind of goes along with all this stuff.
And Terry, I would just add, there's an amazing, there's a set of books about this, but the one that I would point people to if they're interested in this question is this book called Assembling the Dinosaur by Lucas Riepel. And it's about the major East Coast museums founded from the mid to late 19th century and their collection of paleontological specimens and display. But the argument he makes there, which is, you also might think, why are these, the richest people in America spending the equivalent of millions of dollars to build dinosaur wings? And is it just that they love what's the story? And he gets in the books there and shows this amazing story, which is about the kind of conversion of finance capital to cultural capital in that moment, that it becomes almost necessary for these robber barons, as critiques are emerging in that late 19th century Gilded Age moment, to convert their capital into something that's a public good. And they often pick science because science is this ascendant, perceived as an ascendant public good in this period. So in a way, the Detroit Observatory is benefiting from philanthropy in a very similar way. Maybe the beginnings of that same story that Riepele has traced out in the late 19th century.
So, of course, John Dewey comes to Michigan in the early 1880s. He's a major figure in your book, Henry. What is the connection between what ultimately becomes Dewey's philosophy and the experimentalism? I mean, he's conducting experiments, and he and others around here are using some of these instruments that you showed on this campus.
Mm-hmm.
And there's a lab in psychology, and ironically, we can find the budgetary appropriation for it by the regents.
Mm-hmm.
And so they're clearly doing all this kind of work. But of course, we don't think of Dewey as really having an impact on that kind of a field at all. We think of it as, of course, a great philosopher of education, et cetera. So what's the connection, obviously in quite a summary form, between his experimental work and the rise of pragmatism, or his writings about science or education or anything else?
He would be the first to tell you, Terry, that it's absolutely direct. It's dependent. He comes out of the world, in fact, that Gary was describing. So he's an idealist philosopher. He's very, he considers himself a Hegelian. It's a complicated Hegelianism, but he's trained by a absolute idealist at Johns Hopkins in the late 1870s, 1880s. So he's coming out of that tradition, but finding his way into experimental psychology in the 1880s and early 1890s. Now, and this is relevant to anyone who's overseen a recruitment or a potential retention of a faculty member, what he ends up, he leaves for the University of Chicago, the new University of Chicago, in 1894. And he has many reasons for doing so, some familial, some about the respect that his wife was, it's a complicated story. But one of the things that he argues is that philosophy is a science. And for philosophy to be a science, it needs a laboratory. And the laboratory, he argues, for philosophy is a school. The school, the funds for the school, running the school at Michigan are not immediately forthcoming. This is what's dangled before him by Harper at the University of Chicago. He can have a school where he could test his theories. This is the famous lab schools that are still open at Chicago to this day, and helps give rise to Bing and these other schools that are at various major research universities, where the kids are both learning experimentally, which is Dewey's big thing, like Maria Montessori, and learning by doing. That's one of the origins of pragmatism as well. But also being meticulously recorded and subjected to various kinds of study and opened up to the developmental psychology when that becomes a subfield. So they are also lab rats in a very specific sense. Anyone who themselves went to lab at Chicago, where the school that Dewey founded, or knows someone, those kids are called lab rats still, as a kind of fond way of gesturing at this experimental origin. So we may be far from thinking of the school as the laboratory for philosophy, whether the university or the kindergarten, but that really is an insight he comes to at Michigan and then finds the funding for at Chicago.
Some of his famous early essays in psychology are actually empirically based. Are they more philosophical?
It's a mix. I would describe Dewey as not really having a taste for laboratory work himself. And this he shares with his, pseudo mentor, William James, who also is responsible for a lot of these major innovations, but who himself mostly couldn't be bothered to do laboratory work. And so Dewey's claims are empirically based. He is credited with founding the Chicago School of Functional Psychology, but it's really his students, colleagues, and followers who are doing a lot of the empirical work. He himself is 100% dedicated to empiricism, to working with the real world and working with kids as they really are, not as they're imagined, right? But I think he himself is more of it might be a legacy of his idealism, or it might be he's a leader and administrator, he doesn't have time for it, but he is himself not in the lab as much as we might think.
So, Gary, I wanted to talk a little bit about the impact of the observatory on that sort of university culture. And I realize this is a complicated subject that not very many people know a whole lot about. But it is the case that I believe, and you can talk a bit about this, that we actually become the home of one of the first sort of scientific journals in astronomy, I believe, or an important one. So what's happening here in terms of Henry's kind of described this transition into this kind of new world of science. Some of that's actually happening here, relatively early, even under Bruno.
Yeah, so Bruno he does introduce Astronomical Notices, which is the first kind of disciplinary journal based at U of M. It's not the first astronomy journal in the country, but it is one that is intentionally intended to be a kind of comprehensive journal, accepting papers from astronomers all over the world. But also he builds into it this kind of popular astronomy component. I mean, there is the opportunity for amateurs to have some presence in astronomical notices. So it's a kind of interesting hybrid. But certainly the first disciplinary journal at U of M. The other thing is one other thing I suppose is that he greatly the astronomy curriculum obviously becomes much more rigorous under Brunoff. I mean, there was an astronomy curriculum that was part of the classical curriculum, which again had to do with basically reading some texts and reciting them back. But he establishes a whole astronomy curriculum from the ground up, basically. And perhaps in some ways, I haven't looked at this really closely, but in some ways, the first kind of identification of a complete set of courses at U of M around a particular science.
No, I'm forgetting, Gary, was Watson Bruno's student or not? I can't remember the connection.
Watson was Brunoff's student. He was his first student, in fact. And in fact, Brunoff was criticized for having a class in which he had only one student. And he said, well, that student was Watson. I mean, Watson was a prodigy and a genius and you know, a man of many talents. You know, as I think you know, I went on to become the second director of the observatory, but a person of very different temperament from Brunoff. I mean, never got his PhD, for instance, never tried to get a PhD, whereas Brunoff was deeply committed to advancing research. Watson sort of always had his eye on what was going to get him the most visibility. You know, it was he was not about to write a textbook like Brunoff's spherical astronomy. Right? That was never going to be something that Watson would do.
So one of the questions that these presentations kind of raise, just in general, is, you know, so we sort of start with a lot of perhaps a fair amount of science being kind of conducted by people that are essentially thinking about things in a kind of philosophically deductive sort of way. And that there's a kind of a period of induction, but then we actually have this kind of theory generation. I mean, what's the relationship, you know, in general, and the sources for the theory and the practice of science as the century goes on? I don't know, Henry, do you want to start with that?
Yeah, I mean, I think it might be helpful to differentiate between a couple of these terms as they were understood at the time, but as we understand them still. So thinking about, you know, what is deduction and induction. So if we think of deduction as the kind of a version of at least the method being used by Tappan in what Gary was describing, though I think it's more complicated when you actually get into, as Gary alluded to, deduction, the way to think about that would be you start with the rule and then you arrive at a case which produces a result. So the classic example is all the beans in this bag are white. And then you pull a bean out and it's white. You say, these beans are white. Right? This bean is white. The rule was that they're all white. That's easy, right? It's kind of, it follows from the original principle. You know the rule in advance. Induction is the opposite. It's so this is often associated, though it's not identical, with empiricism. So that's here's a bean from this bag. It's white. I'm going to induce that the beans in this bag are white. And those are the two. That's the fight you can think about in the early to mid 19th century. The hypothesis generation, the prediction, this new mode, which is famously associated with Charles Peirce and becomes the kind of a version of this experimental method that I described, is this weird alternative that has lots of error baked into it. It's like it's risky in a sense compared to both of these other approaches. And the way to think about that with the marbles would be, all the beans from this bag are white. These beans over here are white. oh, they must be from this bag. And you can see how that could go wrong in all kinds of ways. Maybe they're from some other bag, maybe it's not even right. So you've kind of decoupled the very careful inductive or deductive approach to whatever the phenomenon is. And you're making what were perceived in the early 19th century as wild speculations. And this just becomes allowable, in a sense, for all kinds of political and intellectual, social reasons, but largely because of the rise of these very material checks and balances that we referred to. The rise of peer review, the fact that more and more of these people who are doing this science are trustable because they're employed by certain kinds of institutions, the division of labor within the lab, right? All those very social and labor-oriented developments in science, in a sense, conspire to enable and buttress this new, much more speculative and dangerous approach to science, which is making these wild speculations and then trying to figure out if you can see if they're true or not.
One of the surprising things about the 19th century, and Michigan is part of this as well, is the rapid uptake of Darwinism. What's behind that? I mean, that seems surprising. So you've got pretty much a denominationally organized system of higher education in this country, and yet quite rapidly, there's a shift among scientists. And I don't know whether this reflects what's happening in these sort of non-university settings either, quite frankly. But how does Darwin become so successful so fast in this country? Henry?
Happy to talk about this. In part, he becomes successful in this country only because his contemporary, Herbert Spencer, is successful first. Herbert Spencer is the popular evolutionary philosopher who has a whole universal view about evolution, who's incredibly controversial and secular. And people are titillated by him. He does this amazing, incredibly popular tour in the 1880s of the United States. The robber barons and everyday people are obsessed with Spencerian philosophy in a way that's surprising when we think about late 19th century life as essentially being like a precursor to the Scopes trial, right? That everyone still is denominationally fixed. And it's clearer to us now that evolution should have been a problem in those traditions. The real answer, Terry, is that it wasn't. That, like, in fact, even though Darwin ends up in a kind of agnostic place, and even though Spencer's philosophy is avowedly atheistic, at least in a familiar sense, there's so much shot through both philosophies that is amenable to design-based thinking, right? That God is the watchmaker who makes watches that can make other watches, that, God is overseeing the process. There's enough there and enough wiggle room that you can maintain. I mean, as we know still today, you can maintain whatever system of religious beliefs you want, as long as you're not too specific about for example, the length of the earth, the historical age of the earth. You can remain a devout believer and use evolutionary science in your daily work or as a kind of popular scientific pastime. So I think we come to think of these as controversial because of some very famous moments in which they are put at odds. But your average learned person in the late 19th into the 20th century often can find a way to make both live in their heads, as we do with all kinds of things today still.
Yeah, it's really quite interesting. And of course, the developments of science and the understanding of evolution, cause some people some delincers. So of course, the famous example on the Michigan campus is Professor Winchell, who feels he's got to go back and figure out, given evolution, which he actually believes in, and given the archaeological evidence, which he also believes in, and the geological evidence, how this affects the situation of Adam and Eve. So you've got this hilarious world in which people are trying to work together to put some of these things back together again, and that it can sometimes produce sort of odd effects. But ironically, It's being driven very much by the popularity of these really very, very interesting and kind of profound changes in the scientific in the scientific world.
Yeah, it's interesting. So Spencer, Darwin, others. These are all books in Tappan's library. And here's where it's just kind of a shame that we don't know. We just don't know what his reaction, whether he read them, or what his reaction to them might have been. Would have been curious to know that.
When Tappan left Ann Arbor, as Gary knows, he auctioned off pretty much everything that he had in town, and he put his books in storage in a downtown storefront, and then later those were sold. And so basically, he's quite a neglected intellectual figure. The last biography of Tappan was written in 1936, I think, or something like that.
something
But
like
also
that.
it's because there's no archive, there's hardly a library. The University of Minnesota ended up through a series of developments, but I think buying most of his library, and many of his books and the markings in the books that he read are in the special collections of the University of Minnesota. But he's not been looked at very much now. In part, of course, is because he clearly was not, on the front line of all these things. I mean, he also his conceptions of some of these things. So he's famous for introducing the scientific curriculum at Michigan, but it wasn't exactly clear what that was. And it became this kind of container for everything that was based in English, so that hilariously, one of the first survey courses on Shakespeare in this country was taught in the Michigan scientific curriculum, only because, of course, that was an English-based author. So there was an odd kind of disconnect sometimes. I'm sure everywhere between these different kinds of approaches. I'm going to take a look and see now if we have some other questions from the audience. I want to emphasize people that are coming to the viewing tonight that when you go into the old observatory building, you'll see some of this in the sense in which the observatory was basically built for the observation, for there to be one observer. So you'll see that the couch is set up so that there's one observer in the meridian room, and it was designed, quite a lot for this kind of individual science that Henry was describing. It's not that they couldn't have a team; they did to some extent, but of course, the original building was actually quite small. And so it really couldn't accommodate, and that was a conception, obviously reflecting the conception of time. That's actually, actually pretty interesting to give you a sense of the physical space that science was conducted in these early years is actually quite constrained, as opposed to what would happen later when there was more team-built science and all these different. You had to have more room, had to have labs, all these kind of things that went on. Basically, went on beyond that. So I think one of the parallel kind of developments over the 19th century is the rise of the idea of science as having some kind of objective knowledge and objective standing. And I'm not quite sure how or when that actually happens. Henry, you've talked a little bit about that.
Yeah, I mean, I think one of the ways to think about this, and this is just owing to that book that I mentioned before, which is called Objectivity by Lorraine Daston and Peter Gallison. But I think it's really instructive in thinking about the moment of the founding of the Detroit Observatory as being right on a hinge in the history of thinking of science as objective. So in the 18th century and in many centuries prior, up through the mid-19th century, there was an ideal of what we might call objectivity. But those historians refer to this ideal, which is very different from our own ideal, as truth to nature. And the idea there is, just like Gary was describing, there are these natural laws out there that are discoverable by individuals. But to discover them, you need to kind of mix your labor with the natural world. So the classic example would be someone like Linnaeus or a scientific illustrator drawing a hawk moth, like the one that I showed you a picture of, but kind of changing. So it wouldn't be like a photograph, like trying to draw the ideal hawk moth so that anyone out there in the world would know that they were seeing one, but you're not seeing an actual, the exact reproduction of a hawk moth on the page. So truth to nature means fudging it a little bit as an astronomer, an illustrator, an observer, to get at that ideal underpinning. That all this other stuff is kind of noise, that the noise of any particular idiosyncratic individual is noise. The objective thing is to change the record. Now, you can hear how that doesn't feel like what objectivity means in the late 19th century, because that's what the story that I told gives rise to, is what they call mechanical objectivity, which is basically, that's the opposite of what you want to do. Basically, scientists are required to essentially evacuate their personal human foibles, their self, and become one with the telescope. They are essentially a recording device. The mind is still necessary, but it's like a blank screen upon which, photographic evidence, eventually video evidence, but, early on, just simply like recording the locations of particular stars, you have to be you have to allow as little human intervention as possible. It's the opposite of the 18th century mode. And that's what you're seeing in the context of the rise of astronomy as an observational and then computational science, is the kind of, now, this is really frustrating for the generation in the middle, who are so used to their authority being in their ability to see the true thing behind the veneer of any idiosyncratic individual. But it becomes the calling card of objective science. The new generation basically kicks the older generation out and says they were basically philosophers or artists or liars or cheats. And what you really need is a human who's like this new technology, the camera, who just objectively records what they observe. And that's, I mean, it's a huge transformation, and it's still more or less how we think about objectivity, which is to say lack of bias in the 21st century.
So clearly, Gary, Tappan wasn't making that change.
No, he was not making that change. I might just take this moment to make a plug for the keynote session tonight, because I think that we'll be talking with Brian Nord, who's an astrophysicist working with AI on cosmological questions, and he's done quite a bit of thinking about what is objectivity and what is the place of the human being with respect to the technology and to the observation.
Great. Well, I think that's it for the questions out there, and so I'm just going to ask if there's anything either one of you wants to add at this point.
No, it's so exciting to be a part of this, and it's just a reminder that science is many things. It's beautiful and it's important and it has a complicated history, but it's also always, of course, at least until it becomes automated or robotic, human. And I think that's where the historian comes in.
That's right. And the history continues, right? As you say, I mean, until, not Tappan's view, but I don't see us going back to Tappan's view anytime soon.
Well, thank you both. It was really fascinating and a tremendous ability to put the two stories together in a really useful way for thinking about the moment of the emergence of the Detroit Observatory. Gary, do you want to just give people a preview of the next session?
Sure. The next session is going to be on the impact of the Detroit Observatory in the history of astronomy. And the panelists are Pat Seitzer, who knows a great deal about astronomy at Michigan over the decades, Andrew Rutledge, who has done extensive research into the timekeeping functions as well as all sorts of other functions of the observatory, and Sally Uwe, who will, I believe, be talking about James Craig Watson.
Great. Well, thank you very much. Thanks to everyone in the audience for joining us today. This has been really fun and exciting, and we'll look forward to the next panel. See you later.
Thanks, everyone.
Thank you.